In this tutorial, we're going to present and analyze the obtained results. In the previous video, we learned how to perform both sampling techniques and recorded the number of species we are investigating in a table. So if you choose one of the examples that we have taken, for example, the effect of light intensity on distribution of daisies, here we have the light intensity and the number of daisies. Actually, these results are not enough to draw a conclusion. As scientists, we should carry out a statistical analysis to see if there's a significant difference in the distribution of flowers or if any difference is due to chance. To do so, we should follow the same 4 steps as we previously did. Step 1. Write a null hypothesis. A null hypothesis is a hypothesis that suggests that there is no significant or statistical relationship between certain characteristics of a population. So here the null hypothesis is there is no correlation between the number of daisies on the lawn and the light intensity. Step 2. Choose a suitable statistical test and justify your choice. To do this, we should go back to the following flowchart. As you know, first of all, we should identify the type of collected data. So in our experiment, we collected the number of daisies on a lawn, which is continuous. And since we are looking for a correlationship between two variables, then we're going to use the Spearman's rank correlation test. This test shows the strength and the direction, meaning positive or negative, of the relationship. Step 3. Calculate the test statistic. Since we're using the Spearman's rank correlation test, we should calculate the correlation coefficient. It's calculated according to the following formula. R equals 1 minus squared divided by n cubed minus n, where R is the correlation coefficient, D is the difference between the ranks, and n is the number of pairs of measurements, which is 10 in our experiment. The easiest way to do this calculation is by using a table just like this one. So here we have the light intensity and its rank, the number of daisies and their rank, the difference between the ranks, and the square of the difference. So how do we rank our values? Well, we rank values by giving the highest value a 1, the second highest value a 2, and so on. For example, for the values of light intensity, this value here is the highest, so we give it a 1. This value here is the second highest, so we give it a 2, and so on. However, if we have two values which are the same, like these two here, then they share ranks 6 and 7 and are both given a rank of 6.5. Now, after ranking both the light intensities and the number of daisies, we should find the difference between ranks by subtracting each rank for number of daisies from the rank for light intensity. Then calculate the square of the difference. So after filling the table, it becomes easier to calculate the correlation coefficient. It's simply 1 minus 6 multiplied by the sum of these values divided by 10 cubed minus 10. So the answer is 0.945. Note that the correlation coefficient will always be between minus 1, which is the perfect negative correlation, and plus 1, which is the perfect positive correlation. And the closer the calculated value is to 0, the weaker the correlation. Now, on its own, this value has no meaning. That's why we need step 4. Interpret the test statistic. To do so, we need to look up the critical value of Spearman's rank for the number of pairs of measurements in a table of probability. In our experiment, the number of pairs of measurements was 10, so the critical value for R at p equals 0.05 is 0.648. Now, if we compare the correlation coefficient value to the critical value, 0.945 is greater than 0.648 at a 5% level. So the null hypothesis is rejected. There is a correlation between light intensity and the number of daisies on a lawn. Since the calculated value is a positive number, it indicates a positive correlation. So as light intensity increases, the number of daisies also increases. Furthermore, when we study a correlation between two variables, we may draw a scatter diagram or a scattergram. The relationship between two variables could show 3 possibilities. Either there's no correlation, meaning there's no relationship between two variables. As you can see in the following graph, the points are scattered. Or a positive correlation, meaning as one variable increases, the other variable increases as well. This is shown by the trend on the graph. Or a negative correlation, meaning as one variable increases, the other variable decreases, as shown on the graph.